Hey everyone, and welcome back. Ready to flex those brain muscles? This time, we're taking a deep dive into the world of shapes, specifically how we wrap our heads around 3D shapes.
And we're drawing inspiration from a really cool textbook, Visualizing Solid Shapes.
Which, I have to admit, when I first saw the title, I thought, oh boy, back to geometry class. But honestly, this stuff is way more fascinating than I remembered.
It's true, we kind of take it for granted, don't we? How our brains just process the three-dimensional world without even breaking a sweat.
Right. Like, I know this coffee cup isn't flat, but how do I actually put that into words? Luckily, that's where the book starts. It reminds us about the basic difference between 2D and 3D.
That's key. It's not just about shapes getting fancier. It's about a whole new dimension literally coming into play.
Yeah.
Depth, or height, as the book calls it. That's what makes something occupy space.
It's like, I can draw a square on a piece of paper, no problem. But to make a box, I actually have to fold and connect, bringing in that third dimension.
And that's where things get really interesting, because the book has this cool exercise. It asks you to look at everyday objects and match them to their 3D counterparts.
It's like, is this coffee cup a cylinder or a cone?
Precisely. It gets those gears turning.
But it's more than just being able to name the shape, right? What happens when we start looking at these shapes from different angles?
Now you're getting to the heart of it. That's where perspective comes in. A single 3D object can look completely different depending on your viewpoint. The book uses this great example of a simple brick.
Okay, I can picture that.
Head on, it's a rectangle, simple enough. But if you tilt it just slightly, boom, suddenly you're seeing depth.
And it's not just bricks, right? The book shows diagrams of all sorts of things, like a hut, a glass, even those complex figures you get by joining a bunch of cubes.
Exactly. And those different views, they're crucial. Because a 3D object isn't just one flat image.
It's like our brains are doing some wild calculations in the background, taking all those 2D snapshots and stitching them together into one solid object.
And speaking of neat visual tricks, have you ever noticed those concentric circles you see when you look down into a glass?
Oh, you mean like how the bottom of the glass looks like it's a smaller circle inside the top rim?
Exactly. That, my friend, is perspective at work. It's all about how we perceive circles in 3D space.
It's like a magic trick for our eyes. But this whole idea of representing a 3D object on a flat surface, it makes me think about maps.
Because maps, they're a whole other ball game, aren't they?
Right. They're not trying to show us exactly what we'd see with our eyes. It's more about showing us the relationship between things, where things are located in relation to each other.
It's about taking a complex, three-dimensional world and somehow squashing it onto a flat, two-dimensional surface.
Without losing the information about where everything is.
Yeah.
And to do that, they rely on things like symbols and scale, right?
Absolutely. And you know what's fascinating? The book talks about how even little kids seem to intuitively understand this difference between a picture and a map.
Oh yeah, like those hand-drawn maps kids make.
Exactly. They have their own little symbols for a house, a tree, maybe even a pirate treasure map with a big X.
And the scale is, well, let's just say it's flexible, right?
But those maps work. They get the point across because they capture the essence of what a map should do. Show spatial information using symbols and relative distances. And that brings us to another crucial concept: scale.
Right, because that tiny little line on a map could represent miles in real life.
It's incredible when you think about it. We're talking about representing vast areas on something that can fit your pocket.
It's mind-boggling. And, it's like that even when we zoom in even further, down to the very building blocks of these 3D shapes.
You're talking about faces, edges, and vertices, the DNA of any 3D shape.
Those are the terms, right? I always mix them up.
Don't worry, the book does a great job of breaking it all down. And it focuses specifically on polyhedrons.
What now?
Polyhedrons. Those are the 3D shapes with flat faces. Like your coffee cup, a cylinder, it's a polyhedron.
Okay, starting to come back to me.
And to really understand polyhedrons, you got to know the lingo. Faces, those are the flat surfaces, like the sides of a cube. Edges are where those faces meet, forming those straight lines. And then you've got vertices, those pointy corners where the edges come together.
Like the corner of a box, got it.
You got it. And the book gets really hands-on. It's great. It has this whole table where you have to count the faces, edges, and vertices of all these different shapes.
So it's like a geometry workout.
Exactly. But here's where things get really mind-blowing. You ready for this?
Hit me with it.
There's actually a hidden relationship between a polyhedron's faces, vertices, and edges, and it always holds true.
Always. No matter how complicated the shape.
Always. And it's captured in this really elegant equation called Euler's formula.
Okay, lay it on me. What's the magic formula?
F plus V minus E equals 2.
F plus V minus E equals 2. It seems so simple.
It is simple, but it reveals this profound truth about how these shapes are structured. It's like a fundamental law of geometry.
Euler's formula. More like Euler's mind-blowing geometric revelation. So this formula, it works for any polyhedron. Like if I took a cube and, I don't know, chopped off one of its corners.
Ah, you're thinking ahead.
Yeah.
That's a fantastic question, and it leads us to the even weirder and more wonderful world of what happens when we start messing with these shapes.
So we're talking about taking a saw to a perfectly good cube. I have to admit, I'm a little nervous for this cube.
No saws required. Just a little imagination. Picture slicing off one corner of the cube, just a sliver.
Okay, like a tiny pyramid coming off, so now it's all lopsided.
Well, it has a name, actually. It's a truncated cube. And get this, if you count up all the faces, edges, and vertices on this new, slightly wonky shape.
Wait, let me guess. Euler's formula still works.
It does. Isn't that wild? You'd think messing with the shape would throw the whole thing off.
But it doesn't. Why not? We literally took a chunk out of the cube.
We did take something away, but we also added new elements. When we sliced off that corner, we created a new face where the cut was. And that new face also means new edges and vertices.
Oh, I get it. So the formula, it's not just about the starting shape. It's about that relationship between faces, edges, and vertices, however they're arranged. That is pretty cool. So this formula, does it apply to any 3D shape I can think of?
It's specifically for polyhedra, remember, those closed shapes made up of flat faces.
Right, polyhedrons. So like a sphere wouldn't work.
Exactly. Spheres and cones, they have those curved surfaces. No distinct faces, edges, and vertices like we see with polyhedra.
It's like Euler's formula is a special tool just for these face-edge-vertex shapes?
Precisely. It's a reminder that even within the world of geometry, there are these hidden rules, these elegant relationships that just work. It makes you wonder what other secrets are hiding in plain sight.
Totally. Okay, so we've gone from 2D shapes to 3D shapes, we've explored perspective, we've messed with cubes, and we've uncovered this secret formula. Where do we go from here?
I think it's time to bring it all back around. How does understanding all of this change how we see the world?
Because it's one thing to read about it in a textbook, but it's another to actually see it in action all around us.
Absolutely. Think about it. Every single object you see, every space you walk through, it's all defined by its shape.
It's like we've hacked into the code of reality. Now we see a building, and we don't just see, like, a wall and some windows.
We see the geometric building blocks.
Right. Like, ooh, that's a rectangular prism, and over there we've got some cylinders holding up that balcony.
And suddenly you're not just looking at a building, you're seeing the thought, the design that went into creating that structure.
It's like seeing the world with X-ray vision, but for shapes. And I'm thinking back to what we were saying about maps, too.
Because that's a perfect example of our brains doing some heavy lifting behind the scenes.
Seriously, we look at this flat piece of paper with lines and symbols and somehow translate that into a mental image of a 3D world.
And we do it so effortlessly, most of the time we don't even realize how complex a process it is.
It's like we have a supercomputer in our skulls crunching all this spatial data. And thanks to this deep dive, we have a little more insight into how it all works. But, you know, understanding the technical stuff is just one part of it, right?
I'd say it's about opening your eyes to the beauty of it all.
Right. Because there's a certain elegance to geometry. It's everywhere we look.
Whether it's the repeating patterns in nature or the intricate designs of human-made structures, there's a story being told through shapes.
It's like we were saying earlier, more than meets the eye. We just needed the right tools to unlock it. So, to our listeners out there, what do you say we take a moment to appreciate the wonder of shapes?
Look around you. Notice the way light and shadow play on those surfaces, how lines converge and diverge to create depth and dimension. It's a whole hidden world just waiting to be explored. Okay,
so we've journeyed deep into this world of shapes, but what's the takeaway for our listeners? What's the point of knowing all this stuff about poly-whatevers and formulas?
Well, it's not just about memorizing terms, right? It's about having a new lens through which to see the world around us.
Because now, every time I see a building, I'm going to be like, ooh, check out that collection of rectangular prisms and cylinders.
And that's great, because you're starting to see the intentionality behind the design.
Right, like someone looked at all these shapes and said, yep, that's going to be one sturdy and stylish building. It's kind of like we've learned a secret language or something.
The language of geometry. And once you start speaking that language, you realize it's everywhere.
It's true. It's like what you were saying earlier about maps, how our brains just do this incredible thing of translating a flat image into a 3D understanding of the world.
That seamless transition from symbol to spatial reasoning is pretty amazing when you think about it.
It's mind-blowing. It's like we all have built-in GPS systems that also happen to appreciate the beauty of a well-placed triangle.
And that's what I hope people take away from this deep dive. It's not just about the technical aspects of shapes, it's about appreciating the art and elegance of it all. The way shapes interact with light and shadow, the way they create a sense of balance or movement.
It's like that quote, "There's more than meets the eye." But now we actually have the tools to see what's hidden beneath the surface.
Exactly. So the next time you're walking down the street, take a moment to really observe the shapes around you. The curve of a lamppost, the angles of a skyscraper, even the humble cube of a sidewalk brick.
Each one tells a story, right? A story of geometry, design, and maybe even a little bit of beauty. Well, on that note, I want to thank you, our amazing listeners, for joining us on this deep dive into the fascinating world of shapes.
It's been a pleasure exploring with you.
And remember, there's always more to discover. So keep those curious minds engaged and keep looking at the world with those shape-seeking eyes. Until next time.